Okay, so potential energy has to do with the energy of position or configuration. So what we're going to concentrate on today is gravitational potential energy. Potential energy, all potential energy is stored energy, and gravitational potential energy has to do with three things. We multiply the mass in kilograms by the acceleration due to gravity times the height. And this will give us how many joules of energy an object has. And so that stored up energy has to do with how high the object is above the ground, how much mass it is, and also the acceleration due to gravity, the pull on it. And so what we talk about with this is the fact that we have the zero level, which is really important here. So in other words, if I had a ball and I had this ball up here, and let's say it's at 2 meters, and let's say the ball's mass is 0.15 kilograms, we would have a certain potential energy. So potential energy is mgh. We'd have the mass, which is 0.15, times g, which is 9.8, times the height here, which is 2 meters. And let's go ahead and calculate that real quick. So 0.15 times 9.8 times 2 is 2.94 joules. Okay. Now, if we take the same ball but hold it over the table, it can't fall as far, right? It can only fall this much. So let's say that's only 1 meter. Well, what's going to happen here? mgh, we've got the mass, which is still 0.15, times 9.8, which is g, times the height, which is 1, we're going to get 1.47 joules. And so 1.47 joules. So, and that's actually exactly half of what it is over here. And so this is just a different zero reference. It still is high, but because it can only fall that much, that's the zero reference, and that's how much potential energy it has there. So when we're solving with potential energy, we have to consider that zero reference. So let's say that there's a boulder here right on the edge of a cliff, and let's say the regular ground continues like this here, but this could potentially fall that far, right? And so our zero reference would be that, and so our height is 42 meters. Our mass is 992 kilograms. So what I want you to do is go ahead and pause the clip and calculate the potential energy of this boulder right on the edge of the cliff, and then you can hit play to continue. All right, so you should have gotten 408,307.2 joules is the potential energy of this boulder according to that zero reference. Now, one of the videos that I like to show, and if you YouTube this, I recommend it. It's pretty fun to see. If you YouTube Lewin, MIT wrecking ball demo, you can see it. It's about 5 minutes long, but he takes the wrecking ball and it goes down. All that kinetic energy turns into potential, or all that potential energy turns into kinetic at the bottom, comes back, and then gets really close to him at the top. Yeah, definitely recommend that. So with conservation of mechanical energy, energy is transferred from one type to another. So as it's transferred, in this case, if you had an object that's high and it falls, that potential would turn into kinetic. Now, without air resistance or friction, the initial energy should equal the final energy. That initial energy should equal the final energy. So you could write out the equation here. The initial kinetic energy plus the initial potential is equal to the kinetic final plus the potential final. We add them up, and all the initial energy starting out should equal all the final. So let's go ahead and take a look at this one together. Let's say we have a ball here that's it's starting from rest, a 10 kilogram ball, and it's a height of 1.5 meters. And we're going to release this ball, and we want to find out what the final velocity is. Well, before we used the kinematic equations, and that's possible here too, but it's good for us to use energy, because sometimes we want to compare the energies. So height initial here is 1.5 meters. The final height, HF, is 0 meters, and that's going to be a new variable for you here, looking at H initial, H final. V initial is still the same, initial velocity, final velocity we've got. So when you write this out, kinetic energy initial plus potential energy initial, doesn't matter which one you start. You could start PEI and then KEI. kinetic final plus potential final, okay? And you don't actually have to write this one out. This one's on your equation sheet. The one you do need to write out is this: 1/2 mv initial squared plus mgh initial, that's all the initial energy, equals 1/2 mv final squared plus mgh final, right? So the initial velocity we know is 0, so we're going to place that in there. The initial height we've got. The final height is, or the final velocity is what we want, and then the final height is 0. So let's go ahead and write that out. We've got those values, so go ahead and write that out, right? We have 0 for the velocity, the 1.5 for the height. We're looking for the final velocity, the final height is 0. So yeah, go ahead and pause the clip and calculate the final velocity when it hits the ground, and you can hit play when you're ready to check. All right, so we should get 5.42 meters per second as the ball falls and then hits the ground. All right, so next, let's go back to the boulder situation. Let's say that this boulder is right on the edge, and you want to make sure it's going to be safe for the people that are coming again, and it's completely clear, and your friends down there, make sure the area is clear, and you're going to push the boulder over and watch it fall. So here it goes, and the question is, how fast is it moving past your friend? Well, let's say that we still have the initial height of 42 meters. The final height now would be 4 meters, right? It's going past your friend, and so go ahead and use height initial as 42, and then height final as 4 meters. And then when you do that, you can find out what the velocity is here. That would be v final, and then we'll assume that it starts from rest. We'll assume that as you push it, it's just a little nudge. No initial velocity. So go ahead and pause the clip and give this a try, and when you're ready to check, you can hit play to continue. All right, so we have our energies. The initial velocity is 0, so we've got that in there. The final height is 4, not 0, because the height right here is 4. We know the initial height is 42. So when we've got that value, we're going to have to subtract 38886 to the other side, divide both sides by 496, and then take the square root. So it's going to be moving 27.29 meters per second at the bottom.